Hey everybody! So today we're going to talk about a few computations that are typically taught in a Calc 3 class. This will most likely be some form of review, but even if it's not, these are important tools for us to have going forward. And I'm speaking about taking the determinant of a square matrix and taking the cross product of two vectors in R3. So let's get into it, starting with the determinant. So what is a determinant? A determinant is a special quantity, right? A special number that we can compute based on the entries of a square matrix M. And when I say a square matrix, what I really mean is that it is an M by M, right? These are supposed to be lowercase m's, just signifying that we have the same number of rows as we do columns, right? So 2 by 2, 3 by 3, what have you. Given a square matrix, we can compute the determinant using the entries of that matrix. And this is really most easily shown by example. So let's take a look at a couple examples here. I'll just quickly note that typically a determinant is denoted using single bars, sort of like absolute value signs around the matrix. All right, so here's our first example. We're going to look at a 2 by 2 matrix. So it has 4 entries, A, B, C, D. 2 rows, 2 columns, and we can compute the determinant of this matrix as follows, right? And this will work, this technique works for any 2 by 2 matrix. I will take the entries on this diagonal, right? So that's A and D, and I'll multiply them together. So I'll get A times D, and then I will subtract the entries that I get from this diagonal, so minus B times C. So we get AD minus BC, and that is the determinant of this 2 by 2 matrix. Oftentimes, this diagonal, sort of the upper left to lower right, is called the main diagonal of a matrix, while the other diagonal is called the off diagonal. So we have the main diagonal AD minus the other diagonal, the off diagonal BC, and that is the determinant. Notice, again, that because this is a matrix, we have 4 numbers in there. The end result is a number. All right. What about a 3 by 3 matrix? All right, so here we have a 3 by 3. It has 9 entries. This will be a little bit trickier. And it turns out that there's a certain recursive element to calculating determinants. To calculate the determinant of a 3 by 3, we will need to be able to calculate determinants of 2 by 2s. And so we'll do this as follows. So first, we're going to look across the top row here. So the top row is ABC. And I'm going to end up with 3 terms in my answer added together. The first term is going to be the first number A times the following 2 by 2 determinant. So I'm going to cross out the rest of this, cross out the rest of this, and then the 4 numbers that are left will form a 2 by 2 matrix, 2 by 2 square matrix, and I'll compute that determinant and multiply that here. All right, so it's going to be A times the determinant of E, F, H, I. All right, and that is our first entry here. Next, we're going to go to B and do the same thing, but we're going to subtract it. So it's going to be minus B times a given determinant. And again, we'll take B, we'll cross out everything else in the row, we'll cross out everything else in the column associated with B, and what's left are 4 entries, D, F, G, I, and those will form, or that will form our next 2 by 2 matrix. And so it will be B times the determinant of that 2 by 2 matrix. All right, so it will be B times the determinant of D, F, G, I. All right, so it was A times that determinant minus B times this determinant, and then finally it will be plus C times the last determinant. So one more time, we'll take this entry, cross out those, and then we'll have these 2 by 2 sort of smaller matrix will take its determinant. So this will become C times the determinant of D, E, G, H. right? And so of course now this is slightly recursive. We have to calculate this by using the entry or the determinants of 2 by 2 matrices. But when all the dust settles, we end up with A times EI minus FH minus B times DI minus FG plus C times DH minus EG. And again, because all of these are just numbers, this whole computation just results in a number. Higher or larger square matrices will work similarly. So to take the determinant of a 4 by 4, you will need to take 3 determinants of 3 by 3 matrices. No, I'm sorry, I said that wrong. We'll have to take 4 determinants of 3 by 3 matrices. So we build a bigger determinant out of smaller determinants, and this quickly becomes computationally wearisome. So if anything is bigger than a 3 by 3, my recommendation is just to use a computer software to do it for you. I mentioned that this is a special number, a special quantity in some sort. That is true, and there will be moments in time when we use the special qualities or special abilities of this special determinant number. However, I'm going to save a conversation about that for another time later in this class, and of course we talk a lot about this in linear algebra. All right. The biggest reason that we introduce the determinant in this moment in time is because we use the determinant to calculate the cross product of 2 vectors in R3. So remember, going back to vectors in R2, we had ways to add them together. We had the idea of scalar multiplication, so that was a vector times a scalar number, but we didn't exactly have vector times vector, right? Instead, we had the dot product, which was a related idea. Here, we have another related idea, the cross product. Unique to 3-dimensional space, we can take the cross product of 2 vectors, A and B, in R3. It gives us a computational way to quote-unquote multiply them together and to get a new vector as a result. And it turns out that this cross product has a great many geometric properties to it, which will be important for us going forward. So first, how do we actually compute this? Well, I'm going to write my 2 vectors. So if I take A and B, these are 2 vectors now, A and B, and I write them like this. So A will have 3 entries, A1, A2, A3, B, B1, B2, B3. Then A cross B will be the following. I'm going to write a 3 by 3 determinant, I'm sorry, a 3 by 3 matrix, or at least a matrix-looking object. And I'm going to do this as follows. Actually, let me change my color back to black. Let me switch this to black. OK, so I'm going to do this as follows. I'm going to put my A entry, right? That was my first element in this cross product. That's A1, A2, A3. I'm going to put that across the middle. Of this matrix. Similarly, B1, B2, B3, I'll put that across the bottom. And for the top 3 elements, rather than put a number, I'm going to instead put my important principal vectors in R3, my I, J, and K. And the idea is once I've set up this sort of matrix-looking object, I'm just going to take the determinant of it, right? Now, of course, a matrix, we're supposed to have all of the entries be numbers, so this is, not really taking the determinant of a matrix as we might like, but we're going to do the same computation, right? So we're going to take I times the determinant of the smaller 2 by 2. That will be I times A2, A3, B2, B3. Minus middle entry j, so minus j times the determinant, scooch over a little bit, times the determinant of A1, A3, B1, B3, plus k times the determinant of A1, A2, b1, b2. Right, so just following our same computational strategy for computing the determinant, we get this. And this will result in I times a given number, right? So that will equal, when I calculate this number, that'll be a2 b3 minus b2 a3, right? All of that times I minus, what is this? a1 b3 minus b1 a3. Right, all of that times j, and then plus, we will have a1 b2 minus b1 a2, all of that times k. Right, and this of course is not anything you'd want to memorize. Really, this process is the way to go about doing this. But notice we end up with a number times I minus a number times j plus a number times k. And because I, j, and k formed our orthonormal basis, this will describe a unique vector in three-dimensional space. And so the end result of our cross product is, in fact, another vector in R3. OK, so that's all well and good, but what is the use of this cross product? It turns out it has a lot of uses, and we'll see it pop up from time to time throughout the semester. For now especially, here are some useful facts. Starting with the bottom, actually, and working our way up, this is suggesting that that our cross product behaves nicely with respect to scalar multiplication. In other words, if I take a scalar multiplication in this parenthesis and then a cross product, I'll end up being able to factor out that scalar. So that factor here factors out, which is great, and what we might expect from an algebra system. Up here, we've got that another sort of useful fact, what we might expect from an algebra system, which is that addition distributes across multiplication, or in other words, vector addition distributes across cross product in the way that we might expect. This is the weird one, right? When we are used to looking at multiplication in general, we're used to seeing that multiplication is commutative, right? That a times b equals b times a, or a times b equals b times a. So in particular, the cross product is kind of interesting because it's not commutative. It's actually anti-commutative. If I flip the order in which I multiply my two vectors, I introduce this negative sign. So a cross b is equal to negative b cross a. And that's just pretty wild. Finally, we have a geometric interpretation of the cross product, so that we had that long computation, but there's a way to interpret what's happening geometrically as well. And specifically, if I have two vectors, a and b, then a cross b will be the unique vector that is perpendicular to a and b, to both of them. Right? So it'll be perpendicular. The direction of it, the direction of this cross product, the resulting vector, will be determined by the right-hand rule. Right? So if a is pointing in this direction and b is pointing in this direction, then by my right-hand rule, I could take a and b, and then a cross b will be in the direction of my thumb, just like we determined x, y, and z earlier. We've got a, b, and a cross b. So we have the perpendicularity, we have the specific direction, and finally we have the length of a cross b. And the length of a cross b is actually equal to the area of the parallelogram that's spanned by a and b. Sort of bizarre, but true. And we'll get a little more into this later. Right? So here's an example. Let's say we took the vector 3i and wanted to cross it with the vector 2k. Right? Well, we have a number of ways that we can do this. Let's start computationally. Right? And if we do this computationally, we had that 3i is equal to 300, 2k is equal to 002. And so to take the cross product of these two vectors, what I'm going to do is I'm going to, so 3i cross 2k right? Setting up this big matrix, right? I could take I, J, K across the top, 3, 0, 0, 0, 0, 2. And then I would take the determinant of this. So for my I entry, right, this would be I times the determinant of what's left over, that's 0, 0, 0, 2, minus J times the determinant of what's left over. What's left over will be 3, 0, 0, 2. Plus, right, what we end up with here is a K times the determinant of what's left over, and what's left over will be 3, 0, 0, 0. Okay, and then when the dust settles, notice that this determinant becomes 0 minus 0, so that's 0, I, minus, this is 6 minus 0, so minus 6j, plus, and this is 0 minus 0, so 0k. 6i minus, I'm sorry, 0i minus 6j plus 0k, we end up with just negative 6j, or 0, negative 6, 0 as our answer. So 3i cross 2k is actually equal to negative 6j. A perfectly valid, if not slightly dull to watch, computation. There's a, again, geometric way to calculate this as well. So let's do the same example. The answer we already know is negative 6j. And so here is the same example, but geometrically interpreted. First of all, the direction, we know that it is perpendicular. We know that the resulting cross product is perpendicular to both 3i and 2k. So here's 3i coming out of the board. Here's 2k going straight up. The directions that are perpendicular to both of those are going to be the directions that coincide with the y-axis, right? So either this way somehow or this way somehow. One of those two. Both of those directions are perpendicular. The actual direction that we care about will be determined by the right-hand rule. Specifically, taking my right hand, I'll point out in the 3i direction, curl my fingers in the 2k direction, and my thumb is pointing in this direction. So that will be the direction of the cross product. Specifically, it will be this direction in the negative y direction will be the resulting cross product. And to determine the length of the cross product, let's go ahead and find the area of the parallelogram spanned by these two vectors. In this case, it's really easy because this parallelogram is actually a square. Right? It might not look like a square, but remember that this is a perspective drawing, so it's going 3 units straight out and 2 units up. Right? So it is in fact a square, maybe a square, but like the wall of a house. And that square has a base of 3, a height of 2, and so its area is actually 6. And so our answer is going to be a vector that points in the negative y direction and has 6 units of length. In other words, we're back to negative 6j as our answer. So the cross product, and more broadly, determinants of matrices, will come up again and again throughout this class and throughout mathematics in general.